The data link layer focuses on the node-to-node transfer of data between adjacent connections. These network nodes can consist of various devices like computers, routers, and switches. The data link layer is only concerned with providing transport from a single node to another node. A higher layer protocol then chains together these short hops to transmit messages across networks. The data link layer abstracts away the need for other layers to care about the physical layer and what hardware, whether it be twisted pair, fiber, or wireless, is in use. In this example, there are 4 independent data link layer exchanges necessary to send a message from host 1 to host 2. Within the OSI model, the data link layer can be further subdivided into 2 sublayers: the logical link control, or LLC sublayer, and the media access control, or MAC sublayer. The media access control sublayer controls the hardware responsible for interactions with the wired, optical, or wireless transmission mediums. It translates data into signal. When receiving signal from the physical layer, the media access control is in charge of converting that physical signal, whether it be electrical current, optical light, or wireless radio frequencies, into bits, and arranging those bits into frames for the logical link control. It must also do this in reverse. When transmitting data, the media access control receives a frame from the logical link control and is in charge of converting that frame into a physical signal. On top of the media access control sublayer is the logical link control. The LLC sublayer acts as an interface between the media access control and the network layer. It receives a message from the upper layer protocol, usually IP packet, chooses which network interface, or NIC, to send the data out on. For example, on a laptop with both wireless and Ethernet capabilities, Ethernet is typically chosen by the operating system. If necessary, it performs multiplexing, which is used to ensure multiple network layer protocols can coexist. Multiplexing is the process of combining multiple signals from different sources into a single usable one. Finally, it wraps the message with the appropriate header and sends it to the MAC sublayer to be sent out. The entire process is performed in the reverse when receiving a frame from the MAC sublayer. The transmission medium will determine the required header. The encapsulated packet is called a frame. In modern applications, there are 2 major family of protocols, each with their own headers: 802.3, or Ethernet, and 802.11, or Wi-Fi. Each of these protocols has had multiple iterations over their existence, with each upgrade changing a 1 or 2 letter suffix, for example, 802.11a, b, g, and ac, and more recently 802.11ax, or more commonly referred to as Wi-Fi 6. Historically, we also had a protocol specifically for fiber connections called Fiber Distributed Data Interface, or FDDI, but it is now obsolete, replaced with Ethernet over Fiber. In the next section, we will go into the details of the Ethernet frame, but it's important to keep in mind on a high level how frames work and why we need them. We've already mentioned that the data link layer deals with the node-to-node transmission of data, and that multiple exchanges are used in conjunction with a higher layer protocol to deliver packets across the internet. In order to get a message from one device to the next, we need to specify additional information. For example, who the sender is and who the receiver is. This type of meta information is what the frame is composed of. It is just header information that is added by the LLC sublayer in order to ensure the delivery of a message from one node to the next. At each hop along its path, the header information is discarded. This is because the goal of the data link layer frame is completed once it arrives on the next device. The information regarding where its next hop will be is stored 1 layer above inside the network layer header. We'll come back to this in a later lecture regarding routing, so we can black box it for now. Once it's chosen its next hop, a new data link layer frame is then generated, whether it be Ethernet or 802.11. all the fields are recomputed using the current hardware device's properties. This is for scalability reasons. Our network may have hundreds or even thousands of devices connected together, but our frame size will always remain constant, no matter the number of hops required. The Ethernet frame is a family of frames that is used for wired connections, both copper and fiber. It contains 6 or 7 fields, with each frame separated by an interframe gap of 12 bytes for synchronization purposes. We'll be looking at the Ethernet 2 frame structure. There are minor changes in the IEEE Ethernet standard used today, which we need not concern ourselves with. The first 8 bytes of an Ethernet frame are the preamble, which is a series of alternating ones and zeros used to synchronize clocks by detecting the transmission rate. The last byte of the preamble, called the start frame delimiter, or SFD, has its last bit changed to a 1 to indicate the start of the next section. The next 2 fields are addressing fields. Addressing on the data link layer is done via the MAC address. The MAC address is a universally unique field used to represent all devices in existence. It is a 48-bit number, which gives us 281 trillion combinations. Each network device is assigned a unique MAC address by its manufacturer. To prevent name collisions between manufacturers, each MAC address is composed of 2 parts: a 24-bit organizationally unique identifier, or OUI, followed by a 24-bit vendor-assigned portion. Manufacturers of networking hardware coordinate with the IEEE and are allocated blocks of OUI numbers, under the condition that each networking device has a unique MAC address. It is possible to tell who manufactured a device by looking up its OUI. To do so in Windows, open up PowerShell and type in the command ipconfig/all. If on a Mac, type into terminal network setup -list all hardware reports. You're looking for a 48-bit number, called the physical address, typically represented as 6 sets of hexadecimal pairs separated by dashes or colons. The first half of that number is the organizationally unique identifier. We can put that number into a search engine or OUI repository website to find the manufacturer of your networking card. In this example, Microstar International was the creator of my Ethernet NIC. Many devices will have multiple MAC addresses if it supports simultaneous communication. For example, routers and switches will have a separate MAC address for each physical port that exists on the device. A computer that can communicate via Ethernet and Wi-Fi will have separate MAC addresses for each networking card. You may also have one or more software-based MAC addresses if you are running a virtual machine or VPN. In the past, there were other addressing mechanisms on the data link layer, like DECnet, but as these addresses were assigned by hardware manufacturers, having multiple competing standards was not a good idea, and the MAC address became the industry standard format used by all data link layer protocols. Most routing is unicast, where there is a single sender and receiver, but there are 2 special categories of addresses. The broadcast address allows a message to be sent to the entire network. The broadcast MAC address is the address with all its bits set to 1, or FF, 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 FF. Any switch on the network that receives a frame containing the broadcast address as the destination will replicate and forward the frame to every other device on the local network and is used in discovery protocols like ARP. Certain MAC addresses are reserved as multicast addresses, or one sender to many recipients. For those interested, I've linked to a list of address ranges, but you won't be quizzed on specific values. Instead, it is more important to understand how multicast works. Multicast addresses allows devices to send messages to a subset of the network. This is done by configuring switches to accept or reject messages from a specified multicast address. Upon receiving message with a multicast address, They will only forward it if the switch has been configured to accept messages for that specific multicast address. The IEEE 802.1q is an optional 4-byte field that provides support for VLANs and quality of service, or QoS. VLANs stand for virtual LAN. They address the problem of having complex networks where the physical topology may not match the virtual. With VLANs, we can create multiple private networks that utilize the same physical network. Imagine a company intranet with hundreds of people that work on different floors. To ensure security, each department must have only its members connected, but they may be spaced apart on different floors. VLANs let you have multiple logical local area networks operating on the same physical equipment. When a message is designated for another device on the same VLAN, it will get tagged with a special VLAN header. Any frames with a VLAN tag will only be forwarded out of a switch interface configured to relay that specific tag. Switches won't forward tagged messages to endpoints not configured to receive a specific VLAN tag. This way you can have multiple virtual networks that may operate using the same physical network. As an example, you can have one VLAN for accounting and another for human resources. The standard also provides support for quality of service, or QoS, to allow your network to specify which VLANs will take priority should frames need to be queued or dropped entirely. Voice over IP, competitive gaming, stock trading, and other time-sensitive applications might be prioritized over file transfers. The ether type is a 2-byte field used to indicate which protocol is encapsulated in the payload of the frame. An ether type value of 0800 signals that the frame contains an IPv4 datagram. An ether type field of 0806 indicates an address resolution protocol, or ARP frame, which is a protocol used to bridge the data link and network layer, which we will discuss later. An ether type field of 86DD indicates an IPv6 frame. Next is the payload, which can be between 46 and 1500 bytes. This is the content that is being delivered, typically an IP packet. Finally, we have the frame check sequence, or FCS, which is a 4-byte field that provides data integrity. The frame check sequence uses a 32-bit cyclic redundancy check algorithm, or CRC32. Before data is transmitted onto the wire, it takes all the data and passes it through the CRC32 algorithm, which produces a digest. This digest is then appended to the end of the frame. Before data is transmitted on the wire, it takes all the data and passes it through the CRC32 algorithm, which produces a digest. This digest is then added to the frame. On the receiving end, the CRC32 algorithm is run again on the received data, and the computed digest is compared with the one inside the frame control sequence. If they don't match, there was something corrupted and the packet gets dropped. The frame check sequence only provides data integrity. There is no recovery aspect built into it. That is handled by a higher layer protocol. Now that we have a basic understanding of what is inside an Ethernet frame, we can discuss switches in more detail. A network switch is a data link layer hardware device that has the ability to inspect frames and forward them only to the applicable party and not the entire network. In the following network diagram, if all the devices were connected via hubs or repeaters, A transmitting to B would prevent D from transmitting to E, as each signal would be duplicated to all endpoints at each repeater. Without CSMA, the messages that B and E receive would likely be corrupted. The switch, however, is able to inspect each frame and forward it to only the physical port associated with the destination MAC address. The ability to inspect the contents of the frame is what makes the switch a data link layer hardware device, in contrast to the hub, which is a physical layer hardware device. In our next lecture, we will introduce the router, which is a network layer hardware device, and as you may have guessed, can inspect the contents of the network layer packet. Switches maintain a memory of attached devices called the forwarding information base, or MAC address table. It stores each known device on the local network. This table has 4 columns: VLAN, MAC address, type, which can be either static or dynamic, and physical port. The job of the forwarding information base is to map MAC addresses to physical ports. That way, when a device wants to send a frame to a specified Ethernet address, the switch knows which port to forward it out on. Port here refers to physical connection on the switch. When we get to the transport layer, the term port is unfortunately used again, but they are unrelated. To avoid confusion, I will use the term physical port when referring to switches, and logical port when referring to the transport layer socket. The switch uses the destination MAC address in the frame, combined with the MAC address table, to look up the physical port, where it then forwards the message. These forwarded messages are chained together until the final destination is reached. Switches learn about attached devices through 2 processes. When a frame is received, the switch will inspect the contents, and if the source address is not currently in the forwarding information base, the MAC address and physical port on which the frame was received will be added. In this example, we have 2 switches with empty MAC address tables. Machine A attempts to send a message to machine D. The first step that the switch does upon receiving a message from A is inspect the frame's source address and associate A's MAC address with port FA04. It should be noted that port names are arbitrary and vendor dependent. If a switch receives a frame from an unknown destination address, it uses a technique called unicast flooding to try to discover the device. A switch will make a request to all physical ports on the network to try to discover who owns the unknown MAC address. Those who do not own the specified MAC address will simply ignore the message. Other switches on the network will first check to see if they have a record of the specified MAC address in their forwarding information base. And if it does, we'll send back the information. Otherwise, the intermediate switch will recursively unicast flood the request. 802.11, or Wi-Fi, operates in half-duplex. Wi-Fi messages are exchanged in data plus acknowledgement pairs. Wi-Fi can be extremely lossy depending on how far away the sender and receiver are. Possibly up to 10% of packets can be lost, and the connection can still be usable. This is generally what the number of bars or signal quality on your Wi-Fi connection is referring to. Because of this large percentage of loss, the frames used for Wi-Fi are different than the ones for Ethernet. It includes mechanisms for acknowledging the receipt of messages. Each wireless station will have a Service Set Identifier, or SSID, used as the human-readable name for a wireless access point, as well as a Basic Service Set Identifier, or BSSID, which is the station's unique wireless identifier, or MAC address of the wireless station. Each 802.11 frame starts with a frame control, which defines the type of frame. Frames are broken up into 3 major categories: management, control, and data. Management frames assist in connecting and disconnecting devices. They include beacons, which are continuously announced by wireless routers, and include SSID, transfer rates, and encryption. Probes. Laptops and phones remember connections they've used previously, so it can run through a list of known networks and send probes out in order to automatically connect next time. Authentication, which are frames used to provide credentials to show that they are an authorized user. And association. Once authentication is complete, mobile devices can associate with a wireless access point to gain full access to the network. Frames used in this context are categorized as association frames. Control frames assist in the delivery of messages and are necessary due to the half-duplex nature of Wi-Fi. They include acknowledgements, which acknowledge the receipt of data, block acknowledgements, which acknowledge receipts of multiple chunks, and request to send and clear to send. Both of these signals are used to combat the hidden node problem. In the hidden node problem, there are three actors, A, B, and C. A and C can interact with B, but do not receive each other's messages. The half-duplex nature of Wi-Fi means that collisions can occur if both try sending at the same time, and data is lost in these cases. Is there a protocol that minimizes this loss? In request to send, clear to send, devices send RTS requests and wait for CTS responses. If it receives a CTS message that is designated for a different device, it will assume that someone else is using the network and will wait a random interval before sending another RTS. This is the same algorithm, carrier sense multiple access with collision avoidance, we discussed in the first lecture, used by the network hubs in the 1970s. These types of algorithms can be used in any half-duplex situation. The next field is the duration field. This is a 2-byte field used by the sending radio to specify how much time it is reserving when waiting for pending acknowledgement frames. There are 4 MAC address fields on each 802.11 frame. The last 2 are optional and depend on the type of frame. Address 1, the receiver, is the device that decodes the radio waves. This is often the destination, but that is not a requirement. This address can be broadcast or multicast address, in which address 3 is checked upon receiving the packet. Address 2, the transmitter, is a device that sends the radio waves. This is required in order to send acknowledgements. Address 3 is used for filtering devices when using a multicast or broadcast address. They ignore messages from BSSIDs that they are not a part of. Finally, address 4 is used for Wi-Fi bridging, which will not be discussed in this course. QoS control and HT control are used to prioritize traffic. Again, voice over IP, competitive gaming, stock trading are all examples of time-sensitive activities, and you might want to prioritize that traffic over a file transfer. Sequence control is a 2-byte field used for authentication purposes. It is not discussed in this course. The payload can be between 0 and 7,951 bytes. Finally, we have the frame check sequence, or FCS. This is the same 4-byte field used in the Ethernet frame to provide data integrity. It also uses the CRC32 algorithm. Our next topic will be the network layer, where we will learn how millions of messages are routed from our local machine to a server, possibly thousands of miles away, all within a few seconds.